Good morning, students. Today we will discuss some more properties related to adjoint matrix. We have already discussed two properties, results, and it is third property. If A is an invertible matrix, then A transpose is also invertible, and inverse of A transpose is same as transpose of A inverse. Meaning if A is invertible, that is determinant A not equal to 0, then A transpose is also invertible, and inverse of transpose of A is same as transpose of A inverse. Now, if A is invertible, determinant A is not equal to 0, and we know determinant A is same as determinant of A transpose. So, A transpose is also not equal to 0. So, A transpose is invertible, mean inverse of A transpose exists. Also, we know a property A into A inverse is equal to A inverse into A is equal to I. If we take transpose of all these three, that is A inverse whole transpose is equal to A inverse A whole transpose is equal to I transpose. I transpose is again I. And we know AB whole transpose is equal to B transpose A transpose. We have discussed it. So A inverse whole transpose is equal to A inverse transpose into A transpose. And A inverse A whole transpose is equal to A transpose into A inverse transpose. Transpose of A inverse. So here again we get AB is equal to BA is equal to I, or XY is equal to YX is equal to I, where X is equal to A inverse transpose of A inverse, Y is equal to A transpose. Then you can say XY is equal to YX is equal to I. So X inverse is equal to Y. So one is the inverse of the another. So inverse of A transpose is same as transpose of A inverse. The property number 4. If A is an invertible and symmetric matrix, then A inverse is also symmetric. You know symmetric matrix? Symmetric matrix is that matrix whose transpose is again the matrix itself. So since A is a symmetric matrix, so A transpose is equal to A. Now, transpose of A inverse is equal to inverse of A transpose, just the previous property. So, transpose of A inverse is equal to A inverse, since A transpose is equal to A. Therefore, A inverse is also symmetric. Mean transpose of A inverse is A inverse itself. Property number 5. If A and B are two non-singular matrices of same order, then adjoint of AB is equal to adjoint B into adjoint A. That arrangement changed. Adjoint of B into adjoint of A. If A and B are non-singular, therefore A inverse and B inverse both exist and not equal to 0. Determinant A not equal to 0, determinant B not equal to 0. Therefore, A inverse is equal to adjoint A by determinant A. B inverse is equal to adjoint B by determinant B. Now, we know AB whole inverse is equal to adjoint of AB by determinant of AB. Now, adjoint AB can also be written as adjoint of AB divided by determinant value of AB into determinant value of AB. So, it is AB whole inverse into determinant A into determinant B, because determinant of AB is equal to determinant A into determinant B. Now we also know AB whole inverse is equal to B inverse A inverse. So B inverse into A inverse into determinant A into determinant B. Now we know the formula for B inverse. B inverse is equal to adjoint B by determinant B. A inverse is equal to adjoint A by determinant A and into determinant A into determinant B. So you will get finally adjoint B into adjoint A. Therefore, adjoint of AB, matrix AB is equal to adjoint B into adjoint A. Now the property number 6. For any square matrix A, transpose of adjoint A is same as adjoint of A transpose. Transpose of adjoint A is equal to adjoint of A transpose. We know when two matrices corresponding elements are equal, then you can say matrices are equal. We will apply that logic. Ijth element of adjoint A transpose is equal to jith element of adjoint A. Therefore, we know cofactors, transpose of the cofactor matrix forms the adjoint matrix. So, jith element of adjoint A is same as cofactor of ijth element of A. That is equal to cofactor of jith element of A transpose. And you can also say this is equal to ijth element of adjoint A transpose. Therefore, adjoint A whole transpose is equal to adjoint of A transpose. Now, the seventh property. If A is a non-singular square matrix of order n, then we can prove determinant value of adjoint A is equal to determinant A whole to the power n minus 1. Determinant value of adjoint A is equal to n minus 1th power of determinant A. We know A into adjoint A is equal to determinant A into I. If we take determinant value both sides, so A into adjoint A whole determinant is equal to determinant value of determinant A into I. We know determinant of AB is equal to determinant A into determinant B. So left hand side will be determinant A into determinant of adjoint A. And right hand side, identity matrix is multiplied by determinant A and we are finding the determinant value of that matrix. So every row has a common factor determinant A and you will get determinant A to the power n into I, because in every column we know also a property k into A, determinant value of k into A is equal to k to the power n into determinant A. Now adjoint A is equal to determinant A to the power n divided by determinant A, which is equal to determinant A to the power n minus 1. Now the last property, eighth property. Here, if A is a non-singular matrix of order n, then adjoint A into adjoint of adjoint A is equal to determinant A to the power n minus 2 into matrix A. Adjoint of adjoint A is equal to determinant A to the power n minus 2 into matrix A, where order of the matrix A is n. We know x into adjoint x is equal to determinant value of x into I. Now if I put x is equal to adjoint A, then you can join A into adjoint of adjoint A is equal to determinant value of adjoint A into I. In place of x we are putting adjoint A. Then you can say adjoint A into adjoint of adjoint A is equal to determinant A to the power n minus 1 into I, just previous property. Now A into adjoint A is equal into adjoint of adjoint A is equal to determinant A to the power n minus 1 into A into I, both sides multiplied by the matrix A. Now A into adjoint A in the left hand side, which is giving determinant A into I, and remaining part keeping same. Adjoint of adjoint A is equal to determinant A to the power n minus 1 into A, because A into I is equal to A. Therefore, adjoint of adjoint A is equal to determinant A to the power n minus 1 divided by determinant A into matrix A, that is equal to determinant A to the power n minus 2 into the matrix A. So these 8 properties are there. Next class we will discuss some problems related to adjoint and inverse of the matrix. Thank you.